take our bodies higher and higher and higher. We can go until the morning glow. We can go higher and higher and higher.
So far we've talked about voltage and current. And to complete the picture for simple electric circuits, we need the concept of resistance. So let's say here's our battery that has some voltage V across its terminals. And we have a conductor and then there will be some current flow from the positive to the conductor to the negative terminal. What is the magnitude of this current? That is given by this expression. The current is the applied voltage divided by the resistance of the conductor. Resistance of the conductor is its ability to inhibit the current. So basically what's going on is that the electrons that are flowing in this conductor will hit the atoms of the conductor and they will be impeded by some amount. The larger the resistance, the smaller the current. The resistance is measured in ohms. This is Greek letter omega. And in fact, if we arrange this in this form, this is called the Ohm's law. So it relates us voltage, resistance, and current in an electric circuit. Let's do this exercise that asks what resistance R should be connected across a 9-volt battery to make a 10 milliamp current. Right, so pretty much we have the situation here. In fact, our voltage here is 9 volts and then the current flows across the resistor or the conductor that has a resistance, and we want to solve for R. So let's start from the Ohm's law, and we want to know the resistance. So that would be V over I. In our case, V was 9 volts and the current 10 milliamps, which is 10 times 10 to the minus 3 amps. And this becomes 0.9 times 1000, so this will be 900 ohms. What happens here is that we start from 9 volts at this point, and across this resistance the voltage starts to drop. A lot of cases people talk about the voltage drop over the resistance. So we start from 9 volts and then this, we could say that we have 9 volts here. Maybe it would be, depending on the resistance of this part, it could be 8.9 or something. But anyway, the resistance drops linearly across the resistor. So here in the half point we would probably have like 4.5 volts, and when we come to the end we would have 0 volts. So that's what the resistance does. It drops the voltage over its length. How do we determine the resistance of a certain conductor or resistor? The relationship is the following. The resistance of a conductor depends on its resistivity, which is a material parameter. The resistance increases as a function of the length of the conductor, and it decreases the bigger the surface area. So let's say we have, or cross-sectional area. So let's see, here we have a cylindrical connector, which is usually the case. It has length L, resistivity of the material, whatever it's made of, and then cross-sectional area A. So we see that the longer the conductor, the larger the resistance, and the smaller the cross-sectional area, the larger the resistance. So if you want to have conductors that have low resistance, we want to keep them short and wide. And it makes sense to have a wide conductor. There's a lot of pathway or bandwidth for the electrons to travel through, so they will less likely bump into each other. And of course, the resistivity, we want to keep that as low as possible for small resistance. The resistivity itself is not constant, it depends on temperature, so we can write resistance is some reference resistance times 1 plus alpha, which is the coefficient of temperature dependence of resistivity, and then some temperature minus reference temperature. So at the reference temperature T0, we have resistivity T0 or rho 0, and then whatever higher or lower temperature that will modify the resistivity. This constant here is positive, so it means that higher temperature will increase the resistivity. And this comes from the fact in conductors that with higher temperature, the molecules or atoms in the conductor, let's say copper, they will vibrate more, and they're more likely to impede the electrons and cause more resistance. And this can also, or resistance has the same dependence, because if we multiply both sides by L over A, we get R here and R0 here. So the resistance of some particular resistor looks then like this. Now we're ready to work on a couple of exercises. The first one asks, which conductor of these four would have the greatest resistance to the flow of charge entering from the left? Well, our resistance is rho times L over A, which means that if we have long and skinny resistor, there the resistance would be highest. So it's going to be this one has the highest resistance. And on contrast, for a low resistance, we want to have L small, A big, so short and fat. And it's this one over here. So this would have the lowest resistance. Then exercise D, a copper wire has resistance of 10 ohms. What will its resistance be if it's only half as long? So pretty much we're cutting L in half, which means it cuts the R in half. So instead of 10, we would have 5 ohms. In exercise E, we need to calculate the length of a wire that would have 1 ohm resistance if we know its diameter. We start as usual, R equals rho times L over A, and we want to evaluate the length A. So this is R times A divided by rho, and the cross-sectional area of cylindrical wire, which is being assumed, is pi times diameter squared divided by 4 and rho. And if we put in the numbers, so R needs to be 1 ohm times pi, diameters 1.5 times 10 to the minus 3 meters, 1.5 millimeters squared, divided by 4 over rho. And for copper, the resistivity is 1.68 times 10 to the minus 8 ohm meters. So room temperature value of resistivity is assumed here. What happens to the units? So ohms cancel, meter cancels one of these m's here. So we are left with value about 105 meters. In the last exercise, we are investigating what happens to the resistance of a tungsten filament in a light bulb when it is at its operational temperature about 3000 Kelvin compared to the room temperature value of the resistance. We know that the resistance depends on the temperature in the following way. So R0, the resistance at room temperature, plus A times T minus T0, where A is the temperature coefficient of resistivity or resistance. And if you plug in the numbers, so we have some R0, 1 plus, and for tungsten, you can find from the tables, the alpha is 0.0045, 1 per Kelvin. And our T is 3000 Kelvin. The room temperature, T0, is 293 Kelvin. So we will get R0 times 13.2, which means that the resistance at 3000 Kelvin is about 13 times greater, or roughly 10 times greater.